In the last example, we were given the function g of x, which was equal to 4x minus 8, and we used that equation to find its inverse, which we found to be a quarter x plus 2. So it turns out there's another method again that we can use, and this time when we're given the graph of the function rather than the equation itself. And usually these questions will ask us to actually graph the inverse. So it turns out that the inverse of a function is just the reflection in the line y equals x. So that's the line y equals x there. It's the identity map, so output equals input. You can see some of the points that belong to the line, like 2, 2, 4, 4, 6, 6, etc. So it's easy to sketch to use as our reference. So y equals x is going to act like a mirror. So we need to find the mirror image of our function about that line. So if we choose a point on our function g then, let's say this point here at 4, 8. So to find the corresponding point, I suppose, on the inverse function, we need to figure out where its mirror image would be. So to do that, we'll go from our point to the mirror and then go out the same distance from the mirror. So it would bring us to about here. And let me do that for one or two other points. So I might take this point here at 2, 0. So go to the mirror and go out the same distance from the mirror. This is very rough because I don't have a ruler. The point would be approximately here. And then another point that will have to belong to the inverse is the point of intersection of our function and the line y equals x. So 3 points really is enough there for me to join them up and have a sketch of my inverse. So there it is, my inverse, a quarter x plus 2. So this method is quite useful then, because we don't have to go and find the inverse then. We just need to sketch the line y equals x and reflect 2 or 3 points about that line and join up the points, and then we have our inverse. Another very common example of inverse functions are the log and exponential functions. And you've probably always known that logs and exponentials are linked in some way, but maybe you never really knew why. And it turns out they are, in fact, inverse functions. So graphically here it's easy to see that they're inverses of each other because they are reflections of each other in the line y equals x. So they're like mirror images. But I also want to show you algebraically why this is the case. I'm going to start with the exponential function y equals e to the x, and I want to find its inverse. So to do that, I need to rearrange this formula to make x the subject. So I want x to be on its own on the left-hand side. Currently, x is a power, so how am I going to get x out of there? Well, if you can remember from algebra, I need to use logs to do that. And because I've got a base e here, I want to use the natural log, or ln. So I'll put ln on both sides. So ln y is equal to ln e to the x. Now I can use my laws of logs to deal with this power. One of these laws tells me that I can bring this power down in front of the log to be multiplied by the log. So that would give me x ln e. Now ln e is just equal to 1. You can check that on your calculator if you're not sure. So then we just have ln y equals x. And we're pretty much done here, except that we want to relabel because we don't want y to be our input variable. We don't want to have x in terms of y, we want the other way around. So y is equal to ln x. and that is the inverse function that we have here. So the natural log function is the inverse of the exponential function. Similarly, if you had the function y equals 2 to the power of x, the inverse would be y equals log to the base 2 of x.